Hi everybody! So in this video we're going to explore different experiments you can do with the Spinel kit from Snellius Minerals. And this kit is great for exploring the optical properties of isotropic materials, as well as understanding how stress can cause our isotropic materials to behave in a less than ideal fashion. The Spinel kit consists of two different pieces of spinel. One is a piece of synthetic spinel created by the flame fusion process. I've cut these into rectangular solids so that there are a couple different views going through the crystal. And these also have one face that has been left rough. This is actually the exterior of the boule that was produced during the flame fusion process. The synthetic spinel samples come in a wide variety of colors and also sometimes display color zoning. Usually the colorant is a bit more concentrated as you get closer to the outside of the boule. In addition to our synthetic spinel, we also have a natural spinel crystal. Our natural spinel crystal allows us to explore the crystallography of spinel, and the crystal form these usually exhibit is an octahedron. Our natural spinel crystals can also come in a wide variety of colors. However, these kits usually have natural spinel crystals that are either pink or red, and this is because we both want colors that we can get enough light through to actually observe the optical properties of our spinel, and also because these are fairly common. So if you'd like one of these spinel kits, you can purchase one at the eBay store Snellius Minerals. The Spinel kit is also excellent to compare and contrast with the corundum kit, so also possibly check one of those out while you're there. So to start our dive into the optical properties and crystallography of spinel, we want to start out looking at the big picture of what's going on with minerals in general. So any particular mineral that we're looking at is going to be defined by its chemistry and structure. The chemistry and structure of our mineral in turn determine the crystallography that we see at the macro scale for our crystal, and also determine the optical properties that we end up seeing as well. For the mineral spinel, our chemistry is magnesium aluminum oxide, MgAl2O4. The structure of our spinel consists of having oxygen in a cubic close packed arrangement, and then having aluminum cations occupy half of the octahedral interstices between our oxygen anions, and having magnesium cations occupying 1/8 of the tetrahedral interstices between our oxygen anions. A good place to check out a structure model of the mineral spinel is a website like Mindat. So the chemistry and structure of our spinel determine the space group symmetry that we'll see at the microscale when looking at spinel. The space group of spinel is F 4(1) over D 3 bar 2 over M. This also determines the point group symmetry that we'll see at the macro scale. The point group for spinel is 4 over M 3 bar 2 over M. Some additional facts about the mineral spinel. The chemistry and structure of spinel result in a material with a relatively high hardness. Spinel has a hardness of 8 on the Mohs scale. The structure of spinel also results in a material with no preferential direction of bond weakness, and as such there's no cleavage in spinel. The density of spinel is fairly high, between 3.5 and 4.1 grams per cubic centimeter, depending upon some solid solution substitutions within spinel. Similar to the mineral corundum, the high hardness, chemical inertness, and relative density of spinel allows it to form placer deposits. And spinel tends to form in a similar metamorphic setting as corundum. So oftentimes, these two minerals are found together. In the past, this has caused confusion, with spinels accidentally being mistaken for rubies. But after looking at the optical properties of spinel today, you'll be able to distinguish these two fairly easily. The solid solution substitutions can cause variability in the density of spinel, and those solid solution substitutions can result in a wide variety of colors for spinels based on a variety of different transition metals that can be put into the spinel structure. Talking about those solid solution series brings us to an important point. There is a mineral spinel, but there is also a spinel group of minerals. The mineral spinel, magnesium aluminum oxide, is a chemical end member of the larger spinel group of minerals, The Spinel group of minerals is of course named after the mineral Spinel. The Spinel group of minerals have common structural properties and come in two varieties, normal spinels and inverse spinels. Let's talk about normal spinel structures first. The chemical formulas of the normal spinels follow the form AB2X4. X represents an anion in a cubic close-packed arrangement. A represents a cation occupying 1/8 of the tetrahedral sites in that cubic close-packed arrangement of anions. And B represents a cation occupying half of the octahedral sites in that cubic close-packed arrangement of anions. Our inverse spinels have a very similar chemical formula of Ba(X4). In this structure, our X anions are in a cubic close-packed arrangement as well. However, the A cations are occupying 1/4 of the octahedral sites, and the B cations are split between occupying 1/8 of the tetrahedral sites and 1/4 of the octahedral sites. The Spinel group of minerals exhibits extensive solid solution series within it. The most common anion is oxygen. However, our A and B cations can be magnesium, aluminum, iron, zinc, manganese, chromium, titanium. And so very rarely will we find the pure chemical end member that is magnesium aluminum spinel. And if we do find materials that are near that chemical end member, they can often be a wide variety of colors depending upon what else has been substituted into that spinel structure. So is spinel the mineral a normal or inverse spinel? Let's go back to our description of the mineral spinel's structure. And given the placement of aluminum and magnesium into our structure, we find that spinel is a normal spinel, which kind of makes sense if you're going to name the entire group of minerals after spinel. So let's take a moment and examine the crystallography of our natural spinel crystal from our spinel kit. We're also just using normal ambient light for this, no fancy lighting conditions here. So here's our natural spinel crystal. This one happens to be from Sri Lanka, and the crystallographic form that we're seeing here is classic for spinel. This is a little octahedron. So our point group for spinel is the most symmetrical of all the point groups. It's 4/m, 3 bar, 2/m. And while I'm fiddling around with this crystal, I want you to start thinking about the different symmetry elements that you can notice in these different views. We should be able to identify 3 fourfold rotation axes perpendicular to mirror planes, and these will be the A crystallographic axes for our spinel. There should also be 4 threefold rotoinversion axes, as well as 6 twofold axes with perpendicular mirror planes. So let's get to work identifying these symmetry elements, and what better place to start than the symmetry element that we're looking at right now. The crystal face that we're looking down onto at the moment looks rather triangular, and if you were to guess that this is one of our threefold rotoinversion axes, you'd be correct. But let's make what's going on here a bit more obvious. This dot represents the threefold rotoinversion axis that we're looking down. And the way we can tell this is actually a threefold rotoinversion axis and not just a regular threefold axis is by thinking about the crystal face that is opposite the crystal face we're currently looking down upon. The outline of the opposite crystal face looks like this. And so we've found a threefold rotoinversion axis running through our crystal in this direction. Our threefold rotoinversion axis is running perpendicular to this pair of crystal faces. Here's the appropriate symbol for our threefold rotoinversion axis. The point group for spinel has 4 of these threefold rotoinversion axes. Our spinel octahedron has 8 crystal faces, and each pair of parallel faces has a threefold rotoinversion axis perpendicular to them. So here are the locations of our 4 threefold rotoinversion axes. Alright, so we've spotted the 4 threefold rotoinversion axes that are part of our point group 4/m, 3 bar, 2/m. Now let's hunt down the 3 fourfold axes with perpendicular mirror planes that are going to actually be our A crystallographic axes. So we'll now look at our Spinel octahedron from point to point, or apex to apex. And when we look at the Spinel crystal in this view, what I hope you notice is a fourfold rotational axis. This axis is also perpendicular to a mirror plane. Here's the fourfold axis represented by a square. As this fourfold rotational axis is going from apex to apex of our octahedron, we can then recognize that there's going to be a similar fourfold rotational axis from this apex to apex of our octahedron, as well as from this apex to apex of our octahedron. And these fourfold axes perpendicular to mirror planes are also going to be our acrystallographic axes. So hooray! We've found our acrystallographic axes and now can understand the orientation of our Spinel in space. Just a note, as we are in the isometric crystal system, all of these acrystallographic axes are the same. Let's go now and hunt down our last rotational symmetry elements for our Spinel. And what we're going to be looking for are twofold rotational axes with perpendicular mirror planes. So taking a look at our Spinel crystal from edge to edge, what we're actually seeing here is a twofold rotational axis. This axis is also perpendicular to a mirror plane. And now that we know our twofold rotational axes go from edge to edge in our Spinel crystal, we can do a bit of math, figure out that there are 12 edges on our octahedron, and so that we must have 6 twofold rotational axes going from edge to edge. I should also mention that we have a total of 9 mirror planes for symmetry elements for our Spinel octahedron. 3 of the mirror planes are perpendicular to the fourfold rotational axes that are our acrystallographic axes, and 6 of the mirror planes are perpendicular to our twofold rotational axes we are seeing here. In summary, we can use our Spinel crystal's symmetry elements to orient it in space like so. And now that we've done a deep dive on the symmetry of this particular Spinel crystal, let's look at some other crystals as well. This crystal is pretty similar to our original crystal, however a bit distorted. But for this crystal, you can see how much light is being reflected off the surface. It has a very high luster. I think it's usually classified as vitreous. You may also notice these small triangular depressions in the surface of this crystal as well. These are known as etch pits, and their shape and orientation is crystallographically controlled. Here's another crystal with the classic octahedral form, but as you can see, it's a bit worn around the edges. This and many other Spinel crystals are often recovered from placer deposits, as running water and abrasion have worn down this crystal. This next crystal's form might be a bit confusing. However, what we have here is effectively an octahedron. However, this octahedron hasn't grown equally along all of its octahedral faces, and so we end up with a crystal that is shortened between 2 of the octahedral faces. However, we can figure out that this is actually an octahedron by using the law of constancy of interfacial angles. And that statement is worth a nerdy video in its own right, and so I will hold off on going any further into detail there until sometime in the future. Also, I wanted to mention again that the color of Spinel doesn't have to be pink or red. These are just the crystals I had available to me for making this video. All the solid solution substitutions of the transition metal cations into Spinel can make it a wide variety of colors. So I've got one more example of Spinel to show you, and this Spinel has something special going on. This next Spinel is twinned, and it's twinned according to the Spinel twin law. So what you are effectively seeing here is 2 Spinel octahedra stuck together along an octahedral face of our Spinel. So the composition plane of our Spinel twin is the 1-1-1 octahedral face. And the reason why this is called a Spinel law twin is because this type of twinning is common in the mineral Spinel. It's nice when things make sense. So you should also note this Spinel law twin is a bit gnarly. It's not the best looking Spinel law twin I've seen, but it's the one I had available to me, and so we're going to roll with it for now. Back to the big picture of what's going on here with Spinel. We've explored the point group symmetry of some macroscopic examples of Spinel crystals. Let's take a look at an attempt for a structure model to help us understand what's going on at the microscale in our crystal. The structure model we're going to take a look at is only going to represent the oxygen in the Spinel structure, unlike our corundum structure model, which we go into great depth to describe in the video Optical Mineralogy Big Picture. The Spinel structure model requires a bit more delving into various Pauling's rules other than just the radius ratio concept, and so we're going to try to avoid that for brevity. To start examining our structure model, we have a layer of glass marbles held together with hot glue. These marbles represent our oxygen anions and are packed together as tightly as possible in this single layer. So in order to add on the next layer in our structure, what we're going to need to do is take a look at some of the voids that we have in this structure currently to figure out how we can best nestle our oxygen anions together in order to make a close packed arrangement. So for this current layer of our structure model, there are two different types of void spaces. One of these types of void spaces is represented here by a blue triangle. And once we spot one of these, we see there are a whole variety of them in this layer of our structure. But there's also another type of void space represented by this red triangle. And here are the equivalent void spaces throughout the rest of our layer. So in adding on the next layer of our structure, we get to make a choice. We can nestle the next layer of our structure in either the voids represented by the blue triangles or those represented by the red triangles. I'm going to go with the voids represented by the blue triangles. In doing so, we also generate the tetrahedral and octahedral voids in our structure. The voids represented by the blue triangles will now become our tetrahedral sites, and the voids represented by the red triangles will become our octahedral sites. So to help you follow what exactly happened there, here's a map of our void spaces from our first layer, and you can see that our new layer is indeed nestled in to the voids associated with the blue triangles. So in adding on the next layer to our structure, we're going to repeat this procedure. Here are the different types of voids represented by blue and red triangles for this new layer, and the choice of placing the next layer of oxygen anions in the voids either associated with the blue triangles or the red triangles will determine if we have a hexagonal close packed structure or cubic close packed structure. Placing the next layer of oxygen anions in the voids associated with the red triangles would actually just repeat the first layer of oxygen anions that we have, and this would be the basis of a hexagonal close packed structure. We don't want to do this because Spinel is cubic close packed. As such, we can make a third unique layer in our close packed structure by actually choosing to nestle our next layer of oxygen anions in the voids represented by the blue triangles. Let's add on our next layer, and also note this is the last unique layer of oxygen anions in our cubic close packed structure. So once again, we'll bring up the map of the voids from our previous layer so that you can see how this new layer is nestled into them. And indeed, our new layer is lined up with the voids associated with the blue triangles from our previous layer. Just a reminder, the voids left behind associated with our red and blue triangles are becoming the tetrahedral and octahedral sites where our metal cations will reside in this structure. Let's think about adding on an additional layer of oxygen anions. Here's a map of our different types of voids for our current layer. And in continuing the cubic close packed arrangement of anions, what we're going to do now is effectively repeat the first layer of oxygen anions in our structure, and in order to do this, we're going to nestle our next layer into the voids associated with the blue triangles. Alright, so here's our next layer of oxygen anions placed in the void spaces associated with the blue triangles. And now we've effectively done everything you need in order to generate the repeating pattern of oxygen in a Spinel crystal. We'll bring up a map of the previous layer's void spaces to show that we indeed placed our new layer in the void spaces associated with the blue triangles. To cap things off, let's bring in one more layer of oxygen anions to finish up the cubic close packed structure model of the oxygen in our Spinel. Now, let's take a look at the shape we generated. Keep an eye out for symmetry elements as we rotate the structure about as well. People sometimes think I've lost my marbles, but No, I just arranged them in a cubic close packed structure to represent the oxygen in Spinel. So hopefully this shape is fairly familiar to you, and what you should notice is that this is actually an octahedron. So we'd also need to have metal cations in appropriate locations in our Spinel structure model in order to determine the symmetry elements we're seeing at this scale. And the space group symmetry of our Spinel is indeed a bit more complicated than the point group symmetry we see at the macro scale. However, the structure model we have for our oxygen in Spinel does a pretty good job of showing that what's going on at the micro scale is related to what we see in macroscopic crystals as well. And that idea takes us back out to the big picture. Our Spinel is defined by its chemistry and structure. We first examined macroscopic Spinel crystals and the point group symmetry elements that they display. We then built a partial model of the structure of Spinel at the microscale. And now let's take a look at the optical properties of our Spinel. We'll start by examining the optical indicatrix for Spinel. The optical indicatrix is the three-dimensional representation of the refractive indices of a substance. As Spinel is isotropic, the optical indicatrix for Spinel will be a sphere. The radius of this sphere will be our refractive index n, which in the case of Spinel is 1.718. Because the optical indicatrix for Spinel is a sphere, no matter the direction we view through our Spinel, the section we cut through our optical indicatrix will always be a circle, with that circular section having a radius of refractive index n. If you're a bit confused about what's going on with our optical indicatrix, I suggest checking out the video Optical Mineralogy Uniaxial Materials. There we do a deep dive into where the optical indicatrix comes from. The spherical nature of the optical indicatrix for Spinel means that Spinel is actually going to be pretty boring when it comes to its optical properties. Spinel will not be able to exhibit pleochroism in plane polarized light, nor will it exhibit extinction and transmission of light with crossed polarizers for any view through our Spinel crystal. And this is because every view through our optical indicatrix yields the same result, simply a circle with a radius of refractive index n. And because our Spinel is going to exhibit the same optical properties in every view, it also means that unfortunately we can't use our optical properties in order to orient our Spinel in space. To summarize, because our Spinel is only defined by refractive index n, our Spinel doesn't have any birefringence. As such, we won't be able to see pleochroism in plane polarized light, and our Spinel should remain extinct with crossed polarizers in any viewing direction. Now that we've talked about the optical indicatrix for Spinel and the theory of what we should see, let's take a look at some natural Spinel crystals in plane polarized light. So here we have a Spinel crystal viewed with transmitted plane polarized light. The plane polarized light is currently vibrating in a north-south direction in this view. We'll rotate our crystal in plane polarized light now, and I want you to notice how pretty much nothing happens. Yeah, it's not really changing color or doing anything fun, is it? But this is exactly what we predicted from the theory. Because our Spinel is isotropic, it will not exhibit pleochroism. So let's bring in our upper polarizer now and take a look at this crystal with crossed polarizers. And as I bring the upper polarizer in, you can see that the Spinel is at extinction. You can see just the smallest bit of light being reflected off some of the octahedral crystal faces. And now we'll rotate the Spinel crystal with crossed polarizers and see what happens. And the answer is not very much. So as we rotate our crystal, it remains at extinction no matter the rotation. And this is also what we'd predict from our theory for an isotropic substance: no birefringence, no transmission of light with crossed polarizers. Now, to truly confirm that our Spinel is isotropic, we'd want to view light transmitted through our Spinel through various different directions. However, if we change our viewing direction through our Spinel to any other orientation other than octahedral face to octahedral face, we'd have to start to think a bit more about Snell's law and the refraction of light, and also critical angles within our spinel. When our viewing direction through our crystal goes through two flat parallel faces, we don't really have to worry about this that much. And so that's why many of the products that I make are cubes or rectangular solids. It's to simplify the optics and what's going on. So if you'd like to know more about the complications that arise from different viewing geometries, I suggest checking out the video Snellius Minerals Quartz Sphere. And for today, I'm happy to say that the Spinel will be as boring in all its other viewing directions as the one we've seen. No worries, you can trust me. I'm a random person on the internet. To summarize, our natural Spinel crystal does not exhibit pleochroism and also remains extinct when viewed with crossed polarizers. This behavior is exactly what we'd expect from an isotropic substance. And even though the optical properties of our isotropic Spinel are fairly boring, it's important that we can identify substances as isotropic. Once an unknown material is identified as isotropic, the list of potential candidates that material can be is very short. Our isotropic materials only have one refractive index, and so by taking a measurement of this refractive index using a refractometer, we can often identify these materials rather quickly. Also note, for our Spinel, since it is isotropic, there aren't any interference figures that we're going to be able to generate for Spinel. So let's take a look at another Spinel specimen, but now let's examine synthetic Spinel made by the flame fusion process. Here we have a boule of synthetic flame fusion Spinel. I'll rotate this around a bit so you can get an idea of its shape. These are quite similar to the synthetic flame fusion boules of corundum that you can also find. However, the corundum boules are often split down the center in order to help reduce stress. We're currently viewing our Spinel with transmitted plane polarized light vibrating in a north-south direction. So let's rotate it around a bit and see if we can notice any pleochroism. And just like our natural Spinel, not really much of anything is happening while we rotate this. No pleochroism to speak of. We'll reset, and we'll bring in our upper polarizer to take a look at our Spinel boule with crossed polarizers. If our synthetic Spinel is truly isotropic, we would expect it to remain at extinction. And our Spinel boule is pretty close to remaining at extinction. However, there is a bit of light being transmitted through our upper polarizer. And the reason for this is that the manufacturing process for our synthetic flame fusion Spinel results in stress remaining in the material, causing anisotropy. Now, the synthetic Spinel sample in our Spinel kit doesn't consist of an entire boule of Spinel. In order to make what's going on with the optics for our synthetic Spinel sample a bit more straightforward, what I've done is I've taken some boules of Spinel and cut them into small rectangular solids where it's easy to view a couple different directions through our polished samples. Let's examine one of these synthetic Spinel samples in plane polarized light. So 5 of the faces of our synthetic Spinel sample are cut and polished, and the 6th is actually just a portion of the exterior of the boule that the synthetic Spinel came from. Leaving this face rough helps us to understand the orientation of our Spinel sample, and also lets you know that, well, there is a bit of color zoning in many of our Spinel specimens. For this example, the blue colorant is preferentially partitioned to the exterior of the boule. Let's rotate our Spinel sample and see if we notice any pleochroism. And as we rotate, we notice that our Spinel is indeed being boring. No pleochroism here, just as we'd expect from an isotropic substance. Now we'll reset and take a look with crossed polarizers. As we bring the upper polarizer in and the light levels adjust, we can see that something odd is going on with our Spinel sample. We'll rotate the cube a bit and see what happens. What we're observing here results from the mechanical stress remaining in our flame fusion Spinel. If our synthetic Spinel sample were truly isotropic, it would remain at extinction with crossed polarizers. What we're seeing is known as stress-induced anisotropy. And this phenomena can often be seen in things like tempered glass or certain plastics. In fact, one of the main uses of polariscopes in industry is understanding the distribution of stresses in materials that are supposed to be isotropic. Let's take a different view through our synthetic Spinel sample and observe the optical properties in this new view. We are viewing our synthetic Spinel sample with transmitted plane polarized light. Let's rotate our specimen and see if we notice any pleochroism in this view. And our Spinel is still really boring, no pleochroism. To be honest, I don't know if there are any examples of stress-induced anisotropy causing pleochroism in a material, but it would be interesting if anyone knew the answer to that. And we'll bring in our upper polarizer to view our sample with crossed polarizers. And as we rotate here, you can see, wow, that is really not ideal behavior. So why is this behavior interesting to us? Well, if we think back to our natural Spinel octahedron, we realize that we can actually tell the difference between our synthetic Spinel and the natural Spinel based on the presence of stress-induced anisotropy. There are some caveats with this, as not all of our natural Spinel may be stress-free, and there may also be synthetic Spinel produced by methods other than the flame fusion process, and as such they might not necessarily have stress-induced anisotropy. But barring those caveats, the stress-induced anisotropy of our synthetic flame fusion Spinel can help us to distinguish it from natural Spinel. Let's add in a synthetic flame fusion corundum sample from our corundum kit, and we can see how to distinguish our flame fusion Spinel and our flame fusion corundum. Here's a link to the corundum kit video, but the main thing for our purposes here is to note that our corundum is an anisotropic material, whereas our Spinel is an isotropic material, barring the stress-induced anisotropy in both of these things as they are produced by the flame fusion process. So our corundum sample is cut so that we have two views down the plane of the a-axes of our corundum. These views will exhibit pleochroism and the extinction and transmission of light with cross polarizers. The third view of our corundum sample is looking down the C crystallographic axis. This is also the optic axis of our corundum. In this view, our corundum sample should exhibit behavior similar to an isotropic substance, in that there shouldn't be any pleochroism in plane polarized light, and with crossed polarizers, the sample should stay at extinction. But of course, there's some stress-induced anisotropy occurring in our flame fusion corundum as well. So as we rotate our corundum sample in plane polarized light, you'll notice that the color changes from a deeper orange to a much lighter orange. This is a rapid way to tell that our Spinel and corundum samples are different materials, as one exhibits pleochroism and the other does not. Let's bring in our upper polarizer, and we can see that our corundum is at extinction. We rotate the corundum and light starts to be transmitted, and eventually we rotate to 90 degrees from our starting position and the corundum is once again extinct. So the optical properties of our flame fusion corundum are very different in this viewing direction than those of our flame fusion Spinel. Let's change our viewing direction through our corundum sample. So when we look along the C crystallographic axis for our corundum, which is the optic axis for our corundum, we should expect it to behave similar to an isotropic substance. Let's bring in our upper polarizer, and what we see here is that our corundum is indeed behaving like an isotropic substance, however an isotropic substance that has stress-induced anisotropy. Pretty similar to our Spinel from earlier. So we end up with this weird splotchy pattern of extinction as we rotate our corundum with cross polarizers. Transitioning back to plane polarized light, we can rotate our corundum sample and see that there isn't any pleochroism going on in this viewing direction. So let's take a moment now to review what we've learned about the optical properties of our natural and synthetic Spinel, and also how they compare to our synthetic corundum. The optical properties of our Spinel should be rather boring, as our Spinel is isotropic. This means our Spinel is defined by a single refractive index. As such, it should not be able to exhibit pleochroism in plane polarized light, and should remain at extinction when viewed with crossed polarizers in all viewing directions. That's the theory anyhow, and it works pretty well for our natural Spinel octahedron. When viewed with transmitted plane polarized light, both our natural Spinel octahedron and our synthetic Spinel sample do not exhibit pleochroism. When we switch to a view with crossed polarizers, however, we can see differences in the behavior between our natural Spinel and the synthetic Spinel. Our natural Spinel octahedron remains at extinction with crossed polarizers, whereas our synthetic flame fusion Spinel sample transmits some light in a complicated extinction pattern. So our synthetic flame fusion Spinel sample is deviating from our theoretical ideal, and this is because of stress-induced anisotropy. This behavior may allow us to differentiate between synthetic and natural Spinel, barring a variety of caveats. We also compared our synthetic flame fusion Spinel with synthetic flame fusion corundum, and this is a good reminder of the differences between isotropic and anisotropic substances. Whereas our flame fusion Spinel will not exhibit pleochroism in any direction in plane polarized light, there are directions through our flame fusion corundum that will exhibit pleochroism. These directions in this specifically cut sample of corundum are along the plane of the A-axes. These directions also exhibit the extinction and transmission of light with crossed polarizers. The flame fusion Spinel sample, however, just exhibits some weird patterns of extinction and transmission of light caused by stress-induced anisotropy. But our corundum has one viewing direction that will behave very similarly to our flame fusion Spinel, and this is looking down the C-axis of our corundum. So when looking through the corundum in this one particular direction, you could possibly mistake our flame fusion corundum for flame fusion Spinel. In plane polarized light, neither substance exhibits pleochroism, and with cross polarizers, both substances have this weird, wonky extinction pattern going on caused by stress-induced anisotropy. So by taking a look at the optical properties of our natural Spinel, our synthetic Spinel, and our synthetic corundum, we can get an idea how to differentiate these materials, and we also gain an understanding of how stress-induced anisotropy can cause our materials to behave differently from the theoretical ideal. Now let's zoom back out to the big picture of what we learned today and why it matters. So our minerals are defined by their chemistry and structure, and because of this, all of these different concepts in our triangle here are related to one another. And usually if you have any two corners of the triangle, you can figure out the third. We talked in detail about these concepts for the mineral Spinel, and we examined the crystallography and point group symmetry of Spinel by looking at a natural Spinel octahedron. We then built a partial structure model of Spinel by examining how the oxygens are arranged in a cubic close-packed structure, and we examined the optical properties of natural Spinel, synthetic Spinel, and some synthetic corundum for contrast. While the optical properties of our natural Spinel are pretty boring, as our Spinel can't exhibit pleochroism and remains extinct with crossed polarizers, this is actually caused by the great deal of symmetry occurring in our Spinel structure. The high level of symmetry in the isometric crystal system means that these minerals also all are isotropic with respect to their optical properties. Determining that a substance is isotropic is often good for mineral identification purposes. But the downside with our isotropic minerals is that we can't use our optical properties in order to orient our minerals crystallographically, as their optical behavior is the same in all directions through our mineral. We also saw how stress can interfere with the ideal behavior of an isotropic substance by causing stress-induced anisotropy. And this is one way to potentially differentiate between natural and synthetic Spinels. I hope you enjoyed this video on the experiments that you can do with the Spinel kit from Snellius Minerals. The kit consists of a natural Spinel sample along with a flame fusion synthetic Spinel sample, and the colors and shapes of these will vary a bit, but they should allow you to do the different experiments that you've seen in this video. Barring the corundum experiments, you'll have to get a corundum kit for that. And of course, you'll also need a polariscope. You can find these kits for sale at the eBay store Snellius Minerals, and there are a variety of other nerdy mineral kits for you to check out there as well. If you have any questions, comments, concerns, or suggestions, feel free to reach out to us at snelliusminerals@gmail.com. Here is a list of the references I used in constructing this video. Thanks again for watching, and have a great day.